Okay, so today we are going to talk about signature analysis and built-in self-test. These two are actually two different topics. Signature analysis is just a method of testing, and built-in self-test is an option for implementing how are you going to do your testing. Okay, so in the sense of whether the testing that you are going to perform is going to be built into the circuit, and so the circuit, when it is switched on, it should perform a self-test itself. That is one method. Or you are going to apply the test vectors and do the testing. So external testing. So the built-in, but signature analysis and these two are coupled, because typically, of course, signature analysis can be used also in external testing, need not be as a self-test. But typically for today complex systems, when you are doing BIST, built-in self-test, you almost always use signature analysis. So it's sort of a one-way coupling, in the sense signature analysis can also be used for external testing. But in today's talk, I am going to cover both these. What are the issues when you are doing testing is, we said that, what are the procedure we said? You said we first generate test patterns, generate test vectors, apply test vectors, and then compare the results with correct or expected results. So this is the pattern that we are following, 1, 2, 3, and which we have to do this for actually working with test patterns. So but when we do this, you can see what are the issues here. So if the circuit is very complex, your test patterns are going to be very large, and once your test patterns are large, then you have to the storage that is required. One is storage required if you are storing it on chip. If you are storing externally, of course you can store it in the disk, which is a fairly cheap medium to store today, but the time that will be required to test, because you have to transfer from the disk onto one by one. And similarly, if you have a large number of test vectors, you have a large number of results, and you have to read those results, so that's also a cumbersome process, and then compare with the results. Again, there is a lot of storage required. If you are going to do that on chip, then again these results have to be stored, the expected values have to be stored in a ROM and then compared. And at all these places, please remember what is happening is, you are doing many things serially, one bit at a time, because of the, if you are going externally, because of the pin limitation, even when you are doing it internally, because your shift registers, you are not going to access them in parallel mode. You will create a lot of requirement for buses and additional parallel buses and so on. So what you will do is, you are again making the shift registers to be serial and feeding them the patterns, you are feeding them sequentially. So it's going to take a lot of time. As the number of test vectors increases, the number of the time that it takes also increases. So to get over all this, signature analysis is a very, let's say, preferred method. Many systems, complex systems today use signature analysis. Of course, when we talk of signature analysis, what we mean is, just take the cue from what your identification of a person is by the signature. So that's how today all financial transactions, you basically sign a check and then your signatures are stored somewhere, and if required, they are compared with the stored signature to find out whether you have signed it or not. So basically the identification is a signature. So here similarly, the identification is some binary pattern. How this identification is generated? The identification is generated, it could be generated in any manner, but one of the preferred ways of generating is what we are going to today discuss. So the advantage of a signature is test results available in a very compact form. So what you are doing is, you apply a set of test patterns, and from the results that you do not store the individual results, but generate one type of an encrypted number, some number which is a consolidation of all these results, and that particular result becomes the one single number pattern becomes the signature of that. So if that particular pattern matches, okay, what you have to really ensure is, if the device is not functioning, if any of the results that are generated are not correct, then you will get a different pattern, and so you can say that the circuit is faulty. For example, let us say talk of a testing of a combination circuit. We have a combination circuit Let us say it has 5 inputs. So, I apply all these 2 raised to power 5 possible input patterns, so which is 32, and just count this particular function. I count the number of ones that it gets for each of the pattern, whether it's. So, what you are essentially counting is the number of min terms that this function has. If you consider the function, so out of, let us say 32 min terms, let us say this function is output is 1 for 13 of them. So, you count this, you apply all this input and count and see that whether they are 13 ones or not. So, you of course will require a counter to consolidate the result. So, the way you are taking the result and generating it is you are essentially putting it into a counter and counting. And once you compare, so if you say that you are 13, then of course you can say that the circuit is functioning correctly. As we discussed in the last class, there is an aliasing problem. Maybe that particular min term which was expected to be 1 is 0, but some other min term is 1. And because of that, the number actually turns out to be 13, but circuit is still faulty. But we have to make sure that such aliasing is doesn't happen very often. So, if of course let us say that doesn't happen, so this becomes the signature, the now count 13 becomes the signature for this particular function. This is based on the min term. So, similarly one can develop any type of signatures, but typically instead of working with min terms, what we work is, of course there are also techniques which do that, but typically for large functions we do not want to apply all the test result inputs, possible test inputs, and that will be increasing testing time. So, what we do is we apply some random patterns, and we will see that how these random patterns are applied and how also the results are consolidated, the signatures are consolidated. One major advantage of course is the biggest advantage is the result is in a very compact form. Instead of storing results for each test input, you are only going to store one signature. In-speed testing is possible because you are going to apply the inputs again in a process through some counters, some sequence generators and so on. So, they can also generate the inputs at a very high speed. Whereas, if you have to serially shift in the inputs like the way we talked of before in test pattern generation, so obviously you cannot do it in speed. You will actually perform one test and then shift in the next test input, then perform the second test and so on. So, the process will be very slow. So, there are certain errors which show up only during in-speed testing. So, that is another and this is the way this signature analysis things are implemented. We have this PRBS generator, we will talk about that. This is a pseudo random binary sequence generators. These are used for two things. They are used for not only generating the test pattern, but they are also used for generating the test result, and we will see how this can be done. In speed is full speed. Testing in whatever let us say the circuit is to work at 20 megahertz for example. So, then you actually can perform testing working with circuit at 20 megahertz. So, the circuit whatever, so you are not going to slow down. You see, if you are doing let us say feeding in the test pattern, there is a time that is required to feed in the test pattern. So, you will feed in a test pattern, typically serially shift the test pattern in. Remember we said there is a register here, there is some logic here, there is a register here, and there is the scan path. So, my test inputs are stored somewhere. It could be of course off the chip or it could be on chip. That's difference, could be coming from the disk. I will shift in a test vector into this registers. By serially I will shift in and I will get some, let us say 1101. This is the test. I will get there, apply then test, get the result over here, and then serially shift out, and then serially shift in the next test vector, which could be 0101. So, I will do that one. So, after applying the test vectors, I am not actually running the circuit at the full speed and slowing it down considerably. Of course, this particular process when you are applying maybe at 20 megahertz, but a lot of these correlation effects come because when you are actually the numbers are changing, the faults also appear. See, almost all our test patterns we are done with static faults. And we only talked of stuck at faults, stuck at 0 and stuck at 1. We didn't even consider bridging faults. Of course, there could also be dynamic faults. But what happens is, so dynamic faults actually show up many times because there are two lines which are running very close and they are changing at a very high speed. So, there is a coupling that gets generated between them. Two lines which are so close, actually there is a capacitance type of an effect between them. Okay, so this generates a coupling. Okay, so such couplings also result in errors. in faults, and especially in very high speed circuits which are very highly densely packed. Though we have done everything for static testing, but we can still find some faults which occur due to the dynamic testing, because such faults may reflect in terms of a wrong output for a test result, and so that will get tested. We will not know that it actually is not a stuck-at fault, but as far as my output is incorrect, I am going to deduce my circuit is faulty. So many of the things, if your coverage is good, many of the dynamic faults also will get tested. But this will get tested only if these lines are changing at a very high speed. If they are not changing at that high speed, then this will not happen. That's more likely to happen when you do in-speed testing. Okay, so now let's talk about a PRBS generator itself. A PRBS, or a pseudo-random binary sequence generator, which is a very key component in all of these, consists of a long shift register with serial input generated by taking exclusive OR of some of the intermediate inputs. Okay, a number of points that I tried to. So typically what is done is, you take this, generate an exclusive OR, take this, generate an exclusive OR. At number of stages you can do that, and then feed it over here. And take, okay, these are also of course outputs, they are the same outputs. So this, if you look at this pattern, you can actually look at, if you are only looking at one bit, you can also look at this. Otherwise you can look at this pattern, the output that is coming, if you want a longer word length output. So this pattern actually will give you a random behavior. Okay, the issue is, how does it work? Okay, basically if you are working with any n bit shift register, so you have 2 raised power n possible combinations, and any pattern that you will repeat will have the maximum sequence length of 2 raised power n. Afterwards it has to, once, because see this is a fixed circuit, so once it reaches a certain configuration, the next configuration or the next state is predetermined. It will go to the same next state. So basically if you look in terms of the state diagram, it is going to be some state diagram with this. Of course, from the starting point I may reach some point through some transitions, but once I reach this, I will continue to go into this pattern, and this length of this is what I am talking about, and this is the random pattern that I am interested in. Now you can choose this n to be very large, and the n should be large enough, first of all, for the patterns like the randomness that you want. So if you want to know, because you are talking about pseudo random, so the consecutive inputs are uncorrelated, that's what we are really looking for. And so if you, let's say you take this n to be even 100 or 200, so it's a huge number. So and making a 100 bit shift register is not very expensive, because shift registers are, because these single bits which are connected serially with each other are fairly compact designs that can be done. Depend of course upon the complexity that you have. And then you take the exclusive OR. Why exclusive OR? Exclusive OR gate has one property. If you look at either the AND gate, OR gate, NOR gate, NAND gate, any one of them, the outputs are lopsided. Like for 3 of the inputs, the output is the same. Whereas if you take an exclusive OR, if you consider the inputs are uniformly distributed between 0 and 1, the output is also going to be uniformly distributed between 0 and 0, 1. So that's one reason that exclusive OR is the gate that is. So whereas if you choose any other gate, it will essentially not give you this behavior, because for out of the 4 possible inputs, that for the 2 inputs the output is 0, and for the 2 inputs the output is 1. So you choose an exclusive OR gate for generating the feedback. So start from a certain, so whatever value that you start from here, that is called the seed. You start from a certain seed number, and then that seed number is important because it doesn't mean that all patterns are going to be 2 raised power n. Depending upon how you have fixed your exclusive OR, you may get this of various. You may actually have even smaller, something which has only 3 or 4 states. You may also have certain pattern, depends on what you start with. So you have to start from a good seed, and this can be actually be designed. Okay, there are method techniques available, and you can also design it, try it out, and make sure that starting from a seed I get a fairly large. It may not be full 2 raised power n, but even if it is close to that or of the same order, it is good enough. This pattern, and out of this I may not use the whole 2 raised power n, whatever is this length, is this L which is close to 2 raised power n. I may not use all the L, I may use only some fraction of it for my testing purposes. And each time I will start from a seed, and then I will go through that particular pattern. So this is called PRBS. This is a PRBS sequence generator. We will also talk about how do we accumulate the result in a minute, but once we take an example, a BIST example, and show it. I will take the same circuit that I had started with in terms of the scan. A BIST design will typically also look the similar way. Of course, there are some changes. These are going to be much more complex blocks, and I will tell you what these are. So basically the circuit is designed exactly as you would have designed otherwise, except that when it comes to implementing these registers are going to be much more complex. There is no difference in the logic is same. So you design the circuit, you identify where these registers are and modify these registers to be BIST registers. We will talk about what they contain. And of course, apart from that, I also need this scan path. The reason the scan path is required is for getting the signature out and also getting the seed in. Okay, so you have to put the seed in and you have to get the signature out, and that's for that the okay. Now let us talk about what each of these registers do. Each of these registers in a BIST situation is capable of performing 4 different operations. So there is this normal mode. The normal mode, I am calling it the PIPO mode, the parallel in parallel out mode. You can take parallelly the data and so when it is actually not in the test mode but in the normal mode, it's taking the input from here and then giving the output to this, and that's a normal mode. The clocks are not shown here, but of course they are clocks. Then there is a PRBS generator mode. I give some mode input to this register, and this particular register will act like the PRBS generator I have talked of here. It will act like a serial shift register. It will not take a parallel input. It will take a serial shift register, and this feedback will get connected, and this output that is going to generate, this is the same parallel output as here. So this is the same parallel output, but rather than taking a parallel input, it will go into the PRBS generator mode. It will take the sequence, generate randomly the numbers. Now the third mode is a signature capture mode. The signature capture mode is actually very similar to the PRBS mode, except that you again make a serial shift register. You again make, so this is your register. What you do is, this is your logic. You use this logic outputs also for doing the exclusive OR. You can take some inputs from here, like the previous case, and you can take some outputs from this logic. So it's now sitting at the output of some logic, and you can take some outputs from here and use this for generating your next input. So now the next state that you are going to, this particular shift register, the next state that it is going to depends upon not only the present state. In the PRBS generator, it only depends upon the present state. Here it not only depends upon the present state, but it also depends upon the output that is coming from the logic. So now what's the use? So basically, if the outputs that are coming, so if we run this PRBS generator starting from, so you have this, you have one register, and this register is generating the inputs. So it is acting as the PRBS generator, it is taking some inputs, and now you are taking this output. Let's say there is only one output, there could be multiple outputs, doesn't matter. Let's say take 2 outputs. So some outputs, and then you are generating the sequence. So this is your R1, this is your R2, and this is the logic that you are testing. So I start from a seed and run this generator, let us say, for 100 clock cycles. So I will get 100 fixed same input pattern. They are random, but they are same pattern each time because I am starting from the same seed. And I am now running this for both of them together. Both of them are clocked by the same clock. I am running them, both of them, for 100 clocks. Again, I have initialized this, I have initialized this to some value. And after I run it for 100 clocks, I will have some bit pattern stored over here. And this bit pattern is the signature of this logic. If because I am generating the same 100 test pattern inputs and I am also running it for the same configuration starting from the same seed, what I will reach after 100 such clocks will be exactly the same number. Each time I should reach the same number if my circuit is correct. If my circuit is faulty, one of these outputs have to be different for each one of these 100 numbers, and once any one of them is different, then this will go into an entirely different value almost always. Okay, so there is this aliasing problem that there may be a situation that where you actually end up with the same, but almost always you will end up. So that is how the design of this is concerned. You have to, there is some analysis required to design it, but once you design it, so you will end up with a different number, and this becomes the signature of the circuit, and this signature can be tested out against the stored signature to say that whether this logic is correct or incorrect. So now faulty or not faulty. So what is so the procedure, let me underline. What is the procedure, the BIST steps? So now I am talking for this particular circuit. There are two pairs of the two logics which are separated by registers R1, R2, R3 are 3 registers, and all these 3 registers can take each of the 4 modes that we have pointed out. So I start from R1, I put that in the PRBS mode and put R2 in the signature mode, that is consolidation of the signature, because I am first trying to test this logic R1, logic L1, so I put that in the PRBS mode, random sequence generator, and this one in the signature mode, and then generate finite number of test patterns. And once I have generated the finite number of test patterns, I have accumulated the signature in R2, and now I use the scan mode to scan out this result out from the R2. Once I have done it, now I put R2 in the PRBS mode, I put R2 in the PRBS mode and R3 in the signature mode, and R2 PRBS, R3 signature, and again I apply the generate finite number of test patterns, and then put R1, R2, R3 all in the scan mode and scan out the signature of L2 and compile. So in this manner I can repeat whatever are the logic blocks that are available, I can repeat that. So if you really see that, you can see that for a complex logic there is a considerable saving. Let us also consider what are the overheads and what are the savings. Overheads are primarily the complex logic. So each of the simple flip-flops that you had in your circuit has to be replaced by this logic, which will give you this multi-mode operations. Normal mode operation, which was the PIPO operation, parallel in, parallel out, also the operations which are in the test mode, which again test mode is not single mode, it has actually 3 modes in the test. You have the scan mode, you have the PRBS mode, you have the signature mode. So you have to make these registers complex, that is one second. Of course you have to provide the scan path. Third, you have to sit in, this is a completely built-in self-test type of a situation. You have to have some small memory and control logic stored, which will actually take control during the testing, because during the testing I have to generate this sequences. I have to, this also there will be a control that is required, which is different from the control during the normal operation. So I have to have this control logic, as well as I have to have some test result stored. They may be fewer, the amount of memory that will be required will be smaller, but they still I will require to store the signatures, which are the signatures for the correct operation of the circuit, and then perform this control and test out the signatures against this to declare that the circuit is functioning fine. So that those are the, let us say, overheads in terms of the additional area, control as well as the results. But if you really consider what are the advantages over other testing methods, the testing time is very small. For applying 100 test patterns, I will require only 100 clocks, whereas for applying the, let us say, of course you do not have to apply that many test patterns in the TPG case, because the test vectors there are very nicely selected. Here they are more random, so here you have to apply more. But even to apply one, assume that there are 1000 flip-flops, so you actually require 1000 clocks to actually get the pattern into the register, and then apply it, and then again another 1000 clocks to get the result out of the register. So it is going to be much more time consuming to be able to perform a large number of tests in that particular mode. So for this reason, today for complex circuits, when you can actually afford to have this type of an overhead for testing, almost always today the built-in self-test mode is used. Now typically the way the design community works is you actually do the design and then introduce the testing on top of it. That is, you make the design as you are doing, then you replace these registers, introduce the scan paths, and only the final placement and layout part you do it after introducing that. But increasingly people are also looking at techniques where you do that design, which is called design for testability. We are not going to talk about that in this course now. But basically the advantage is you can try to integrate it so that your testing overheads later on becomes smaller. Like if you are making your design decisions, you also look at one of the parameters for design decisions being, one of the objectives could be reducing the overheads that will come because of the testability, which essentially would imply that you may actually be generating some test points, or you may be actually not having that deep logic that you are having otherwise, and so on. So in those ways people also try to integrate testability into the design process. But either way you do, even if you do design for testability or not, you have to finally provide test vectors and either do the design with built-in self-test or external testing. With that we will stop.